So last couple of lectures we looked at the common emitter amplifier in some detail, because that is one of the most commonly used amplifier configurations. Today we will look at the same circuit but without the emitter capacitor, and that is called as a common emitter amplifier with emitter degeneration. And then we look at the common collector amplifier. So to recall, this is our circuit, the amplifier without the emitter bypass capacitor. This is a circuit with the emitter bypass capacitor. So this is called the common emitter amplifier. We've looked at this previously. Let us study this. Well, we studied this a little. I just want to make a few more comments about this circuit this time. So the output at the collector of this circuit with the bypass capacitor, the common emitter amplifier, as we've seen before, is minus GMRC, and also can be written as minus ICRC by VT. I've said this before, but it is important, so that I'm emphasizing again that the gain with CE is large, but it is a function of IC. The gain is a function of IC, and as IC varies, the gain of this circuit also varies. And in fact, if therefore the output voltage swing is large when there is a small input applied, then what happens is that the collector current varies, and therefore the gain of this circuit varies. We had seen this before, but again, so here is the plot we had seen where we had applied a small input at the base and we had looked at the output, and the input, which is a pure sine wave, is the red one, and so I've plotted on top of each other. And what we saw was that on the higher side, at the high end of the output voltage, the output experiences a lesser gain than what is the nominal gain, which was minus 218. And at the lower end, the output experiences a higher gain, and these are due to the collector current being higher here and lower here. So this is a disadvantage of a circuit with an emitter bypass capacitor. The consequence is what I wanted to point out here, is that because the gain varies as the output itself varies, the output voltage is not a very exact reproduction of the input voltage. The output is not a pure sinusoid for an input which is pure sinusoid. So one says that the output is distorted. So large gains, common emitter amplifiers, cause distortion in the output. And of course, distortions are not good in many applications. Alright, so let's look quickly at the output without CE. So there is no CE connected, and we had seen before that if there is no CE connected, this is the voltage gain, and then because 1 plus beta is large, we ignore the R pi, and then the betas cancel, and we get a gain of minus RC by RE. Now the observation we make here is that RC by RE is typically small. It cannot be made very large. Certainly cannot be made 200. Actually, that's a question. Perhaps we'll ask, why can it not be made 200? You think about why this cannot be made 200. But it cannot be. So the gain is not large, but what we observe is that this gain is not a function of the collector current. So even when the output voltage swings to whatever value it can swing, the gain remains constant. And because the gain remains constant, the output is a faithful, more accurate reproduction of the input signal. So these amplifiers, where the gain is small, are much more linear compared to amplifiers that have a gain that is a function of IC. So this is actually a trade-off. Either one gets a high gain or one gets linearity. And as we have seen before, what RE does is it provides or causes negative feedback. And so this is actually one more example of the advantages of negative feedback. We have seen some before, so we are adding one. One thing that negative feedback does is it reduces gain. But along with the reduction in gain, it causes many other advantages. So we have seen it allows for DC bias stability. So much earlier, we saw that it increases the bandwidth of the amplifier. And now we add to this list, it increases the linearity of the circuit. So the output linearity means that the output is an exact reproduction of the input, or Vc is directly proportional to Vs with a constant here. So let's go back. So here IC is actually a function of Vs, because as Vs changes, IC changes. So this is a nonlinear function. Alright, so this circuit without CE or with RE present for the AC circuit is called a common emitter amplifier with emitter degeneration. Alright. Now let us look at the circuit, the same circuit with the output taken at the emitter. So we again looked at this circuit briefly before. We'll discuss this more in detail now. Now again, if you recall, we had said that if we are taking the output at the emitter, then the collector resistance has no value, no purpose. So if you're going to apply the input at the base and take the output at the emitter, then the collector resistance is irrelevant. So we'll remove it. So the circuit we really want to study is this circuit without the collector resistance at all. Now we have analyzed this circuit with RC, but doesn't matter, in lecture 9, and we had found an expression for VE. Let's quickly revise that derivation, and then let us also find the input and output resistance of this circuit, input at the base, output at the emitter. Okay, so this is the derivation I have copy pasted from lecture 9. So you will hopefully recall this circuit. So we had input at the base. By the way, I have removed the collector resistance here as compared to what we did in lecture 9. But this makes no difference to our derivation, because in the final expression for the voltage at the emitter there is no RC. So okay, so we wrote a nodal. Where did we write the nodal? We wrote a nodal at the emitter. We solved it, and we got the emitter voltage as a function of the source voltage. Source voltage, base voltage, they are both equal. Then we had written an expression for the base current. Then I have added to this an expression for the input current, this current. So what is the input current? The input current is three components: the base current plus the currents through R1 and R2. So the input current is Vs by R1, Vb is the same as Vs, so Vs by R1 plus Vs by R2 plus Ib. And Ib we had derived last time is all this, Vs by all this. So this is an expression for In. We'll come back to this in a minute. Let us discuss the voltage gain first. So the voltage gain is V by Vs, which is all this, and as we had seen before, it is approximately 1 because this R pi is very small compared to the 1 plus beta Re, and therefore this is approximately 1. Because the gain is 1, this circuit is often called an emitter follower. Emitter follower because the emitter voltage follows the base voltage or the input voltage. Now if you think about it actually of this circuit, the gain being 1 is not really surprising. Why? Because we are applying the input at the base and taking the output at the emitter. But we know that if the input changes in the input voltage are small, and therefore the changes in the input or the base current are small, then the base emitter voltage of the transistor will remain more or less constant. Why? Because the current varies exponentially with the voltage, and for small changes in base current, the changes in the voltage will be small. So if the base voltage changes by a certain amount, the base emitter voltage remains constant, and therefore the emitter voltage will change by the same amount as the base voltage change. Therefore VB is equal to, VE is equal to Vs or VB, which are the same. So of course then the question is, if the gain is 1, does this circuit have any use at all? So let us see. So let us look at the input and output resistance. So let's look at the input resistance first. So let me go back. So the input resistance is what? Thevenin's theorem. We apply Thevenin's theorem. The definition of the input resistance is the resistance looking into the input terminals of this circuit. And here we have, what is it? So the input resistance is simply, by Thevenin's theorem, the input voltage divided by the input current. So Rin is simply Vs by In, which you know from Thevenin's theorem. Now we've derived an expression for In terms of Vs here. So if you take Vs out, In by Vs, which will be 1 over Rin, is equal to 1 by R1 plus 1 by R2 plus 1 by this quantity, which means that Rin is the parallel combination of R1, R2 and this quantity. So I have written that here. So the input resistance of this emitter follower, where did I mention this is, I'm sorry, I forgot to mention that this is also called a common collector amplifier. Why is this called a common collector? Because if you look at the small signal circuit, the input is between the base and ground, which is the collector. In this circuit, the collector is grounded. So the input is between the base and ground, output is between emitter and ground, collector is grounded. So this circuit is also called a common collector. More often it is called emitter follower. Okay, so we say the input resistance of the emitter follower is R1 parallel R2 parallel 1 plus beta Re plus R pi. So we put numbers here, we get 30 kilo ohms. Now the last term in this expression is important. Generally, as we already saw, 1 plus beta Re is much larger than R pi. Why? Because beta is usually large, and Re and R pi are typically of the same order. So this is like 100 times Re or 200 times Re. So this circuit has the potential of having a very large input resistance if we use dual supply. Now you recall that if you have a dual supply amplifier, then R1 and R2 are not required, and in that case Rin will simply be this last term, and this last term can be very large, 330 kilo ohms for these values, and Re is actually not very large, it is 3 kilo ohms. It can be made larger. Beta can also be larger. So this circuit has a potential of providing a very large input resistance for dual supply. If one uses a single supply, also this can be large, but then one has to make R1 and R2 also large, which is possible. But if you go back to our design of the DC circuit, where we had designed R1 and R2 to make IC insensitive to beta, there were some constraints there. You go back and look at them, and the constraints were such that R1 and R2 could not be very large. So this is a trade-off actually between DC bias stability and input resistance. So if we want a highly DC bias stability, then the input resistance would be not as large, as is the case here. But if you are willing to sacrifice bias stability, then the input resistance can be large. Overall, this circuit can provide much larger input resistances compared to the common emitter amplifier. Let's look at the output resistance. What is the output resistance? Again, we use Thevenin's theorem. We use that second form of finding the output resistance. So what we are asking is, this is our circuit. What is the resistance looking into the output terminals? So what we do is we find the short circuit current. So we find the output short circuit current, and then the resistance between these two terminals will be the open circuit voltage VE divided by the short circuit current, which I have called I out. VE that we previously found when this was open circuited. Of course, in this circuit, VE is 0 because we've shorted it to ground. I probably shouldn't even have written VE here, probably confusing. So please ignore this VE. Okay, so let us see. So how much is I out in this circuit? This is of course a different circuit, so I have to solve it again. So we first of all notice that IB in this circuit. So now this node is at ground. So IB is simply VB by R pi. VB or VS, same thing. So IB is VS by R pi. I out, the current in the short circuit. There is no current in RE because it is grounded to itself. Oops, sorry. Or shorted to itself. So the current I out is equal to IB plus beta IB. So 1 plus beta IB. So I out is 1 plus beta IB. IB we already found, Vs by R pi. So we say I out is equal to 1 plus beta Vs by R pi. Now we already know VE in terms of Vs, which is this, that's already derived. So R out is VE divided by I out. So we write all of this and we get this expression RE R pi by 1 plus beta RE plus R pi. Again we say R pi is small compared to 1 plus beta RE, so we ignore it. So we get, then RE cancels, we'll get R pi over 1 plus beta. 1 plus beta is beta, so we get R pi by beta, which is R pi is Vt over Ib. So we get Vt over beta Ib, Vt over Ic equal to 1 by Gm. So the R out of this circuit is equal to, we either write it as Vt by Ic or we write it as 1 by Gm. Now if you put numbers, so let's remember this expression, R out of the emitter follower is about 1 by Gm. If IC is 1 milliamp and Vt is 25 millivolts, then R out is IC over Vt, Vt over IC, it is 25 ohms. 25 ohms is a rather small resistance. Now in bipolar transistors, it is possible, not easy, but it is possible to get IC to be as large as 100 milliamps, which will make an R out of 0.25 ohms, which is a really small number. So what we have discovered or concluded is that the emitter follower has a gain of 1, but it can have a very large input resistance and a very low output resistance. Or let's say it can be designed to be to have a large input resistance and a low output resistance. So this circuit is used widely as a unity gain voltage buffer. We've seen unity gain voltage buffers last semester. These are circuits that are basically this. A buffer is a circuit that has a gain of 1 and a large input resistance and a low output resistance. So this is where emitter followers are used, and we will in fact use them when we design larger amplifier circuits. Alright, so that is for this lecture. Next lecture we will look at other possible amplifier configurations.